the wonderful world of quantum computing. That's basically what I would like to talk about, and if I can use this device would be great. What you see is a quantum chip that we've started developing in Delft with my colleague Leo Di Carlo. He sounds Italian, but he's actually Argentinian. And with whom I'm working very intensively with the two teams that we have to actually build a first prototype of a quantum computer. And I will hopefully explain a little bit in detail what we understand by that. So let's start by looking at a classical machine. Yeah, and here we see a diagram which is being drawn by someone where we have memory and processor, and we have instructions in memory residing, and of course we transport now instruction after instruction into the processor, and we decode the instruction, which is an addition. Then we get the operands, so the 3 and the 6 in this case, from memory, and we put them again in the local register, we compute the result, and we write back the result, which again in this place will be in the same location as where I retrieved the 3, because that's what my instruction is actually telling me how it should be done. So this is how in principle every single computer, what size and when it was built basically works. And I will try to explain a little bit what happened also, let's say, in the last 20 to maybe even 50 years, and we see a clear trend in downsizing of the technology, so that it's sometimes I have to look around because I don't know what oh, it's already I'm sorry for this. So I see that my scale is going up to the nanometer scale. So one nanometer is 10 to the minus 9 divided by 1 meter, so that's pretty small. And we see here that the compute power which we hold in our hands, which can be an iPad or your smartphone or whatever, has more compute power than, let's say, supercomputers 20, 30 years ago. So that's kind of the trend we see in technology happening still today. Yeah, we all know about Moore's law that's going to end. I will not explain about that, but Intel says, no, it's not going to end. It will end when we don't have any ideas anymore. And that's basically what we try to explain today. So at the far right, you see atoms, and that's indeed the scale at which we're using technology these days. This is the scale at which we are developing things. And even in quantum computing, I will tell a little bit more later on, we're using single electrons, for instance, to represent one which we call a qubit, but I will explain that in a couple of minutes. So where is this, what kind of philosophy or scientific discipline are we basing ourselves on? Is evidently physics. And I show here 3 prominent physicists that you may, well, for sure you've recognized Einstein, because he already mentioned once or twice, I think, in previous talks. And we see the guy on the right, which is Niels Bohr. He's a Danish physicist, and he lived more or less in the same time period as Einstein. And but the scale at which they were reasoning, the phenomena that they were looking at, is completely different. So Einstein, the relativity theory and those kind of things is about gravity and interaction between planets, or large-scale phenomena. And Niels Bohr was more, let's say, at the subatomic scale. And he said, but those concepts are not applicable, at that level. And because quantum, and that's quantum physics, there is a fundamental principle which is randomness, and I will explain that a little bit later on. And that's also why Einstein says, "No, God does not play dice," because he could not imagine that if there is something like a God, that he would assume that there is some random behavior in nature, and therefore also in human beings. And the third person at the bottom is Richard Feynman. And he's an American. He was one of the most brilliant physicists that I think that lived at least in the 20th century, and there were quite a number, of them. And he is actually the initiator. He was the one who formulated in 1982, so that's basically around 6 years before he died. He said, we should build a quantum computer which is based on these quantum phenomena that we want to understand in a very deep way. And therefore, he was proposing that we should look at the technology and think about how to build a device, a computational device. And I will explain those concepts a bit more if I can switch to the next slide, which I can. So what is what makes quantum computers so special? And I hope to give you at least an intuition, a profound understanding. That's maybe very difficult because I still have to find actually the first person that really understands at that level, yeah, how it works. So we are more intuitive, intuitive reasoning rather than very analytical. So what makes these quantum computers so special? Well, again, let's go back to how machines that we have in our daily life that are filled in your car, yeah, that you have on your wrist most likely, or in your pocket, your smartphone, or whatever it is, they are all based on bits, zeros and ones. And then we can combine these bits in multiple sequences so that we can represent bigger numbers, yeah, or we can represent like huge text on which we can then apply all kinds of algorithms. And algorithms are like these standard protocols, well, they're little programs, yeah, that describe what should be done at each step in the algorithm. So that's what classical bits are. Now, when we move into a completely different world, namely the quantum physical world, we have to look at completely different phenomena. And I'm just mentioning here the three that are really key and really fundamental and extremely difficult to make on a large scale. And I will maybe not explain everything, but this is really a big challenge. So it's superposition, measurement, and entanglement, and I will explain those three in the next coming minutes. So here I have a little animation from Idée Quantique, where I have, let's say, an electron that is now in the ground state, and now it's in an excited state. So you see the energy levels, they move discretely between low and high. And now it's in a superposition because you see the two levels are activated, and indeed this electron is in these two states at the same time. Now I have an observation, and there's an eye, so when the eye opens, one of those two superposition states actually disappears. And that's actually where the randomness comes from. Yeah, and this is really key, because that means that when you build a quantum computer, you basically move away from what we know classically, which is very deterministic, very classical. When you do the same algorithm and the same data, you execute it 1,000 times, you will get 1,000 times exactly the same results. In quantum, this is not true, and I will explain that in a couple of minutes. So we use qubits, as I already said. So we don't use these classical bits because they don't have the superposition and entanglement property that we need in order to compute. So we have these qubits which can be in a combined state. So it can be 0 and 1 at the same time. So classically it's either a 0 or a 1 or any combination of those, but it's always in an exhaustive state of one single combination of zeros and ones. In quantum physics, this is absolutely not true. So what I see here is on the left, the 0 part, which is, let's say, the right arrow, the red arrow is pointing above, and the 1 state is the red arrow pointing below. And then you can have any position in between, which is the superposition state. And then depending on what I'm going to, how my algorithm is computing, what it actually is doing, it is manipulating what I'm showing here. Oh no, it's from behind that the projection shows, I'm sorry. So what we do in a quantum algorithm is that we influence the alphas that we see there, the alpha 0 and the alpha 1. And in principle what it means is that the alpha 0 in a way represents the probability when I do the measurement, then the superposition disappears, then with what probability am I going to get a 0, and with what probability do I get a 1? That's what those alphas actually mean. And so all of the quantum algorithms, and so now I will show you that it can be the 1, so that the alpha 1 is bigger than the alpha 0, yeah, then you will, when you measure it, you will measure the 1 result. Now, assume that I have here 80% white and 20% black. So that means I have to execute my algorithm multiple times so that then I can aggregate all of the results, and then I can simply count what result gives me most, is computed in most of the cases, and that's going to be the final result of your quantum algorithm. And that's why we call it's non-deterministic computing, refers to classical computing. So I will briefly say something then about the two other phenomena, which is measurement, as I already explained. It basically means that when I'm in a superposition state, yeah, and I will measure it, I'm going to force it into either the 0 or in the 1 state, always. We have not yet figured out a way to overcome that. And maybe in 20, 30, 40, 50 years, maybe we will, but for now we don't. Yeah? So that is where this non-deterministic element comes from. And then the third property is entanglement. And that's also a very crucial way of combining these qubits. Because the qubit that is in the superposition state basically has two states, has two values, namely the 0 and the 1. And if it's 50-50, then you can get any kind of result at any point in time by measuring, but you can never predict. When it's 80-20, then you know that in 80% of the cases you will get the 0 and or the 0 case, for instance, in this case. So the entanglement is, again, I'm combining two qubits. They're in a superposition here. Yeah, so I basically have, when I combine two qubits, I have 4 positions. And if I have 3, it's 2 to the power 3. I cannot show that with my fingers, yeah, but you have 8 different states. That's what 2 to the power 3. So 2 by 2 by 2, right? Means so this, and then the entanglement is a way of combining them. And then when you apply whatever quantum algorithm on such an entangled state, then you apply it at all of those combinations at the same time. Yeah, it's not only about the entanglement there, but this is really key. So I will briefly show you, yeah, to give you a little bit of an idea where the compute power now possibly comes from. Because, yeah, sure, now, yeah, it depends on how many qubits you will have and whatever it is, yeah, but if I give me 5 or 10 supercomputers, I can do the same. Well, this is not true, and I'll give you an example later on. So here I plot the graph of having 2, 3, up to 10 qubits combined, and then you see here, these are 10, yeah, 2 to the power 10 combinations, so parallel states. And what quantum physics is giving me massive parallelism for free. And the for free should be taken with a little bit of salt, because there's no free lunch here either. But that's the principal idea that we're using. And why is that important? Because if I then execute any quantum gate, and I will show one simple example, on those on this matrix, I apply that particular gate on all of those states at the same time in one shot. Whereas in a classical machine, I would have to do it sequentially. Yeah, and 2 to the power 100, that's already a big number. So it's sequential versus massively parallel. That's what it means. That also implies that if I'm actually building a new machine and I want to say, okay, I'm going to make it more powerful because I need to have more data that I need to process, what I need to do is simply add one more qubit. Because by adding one more qubit, it's 2 to the 2, to the 3, to the 4, to the n plus 1, I each time double the entire number of superposition states that I can manipulate at any point in time. Yeah? So that's what the theory, of course, tells us, right? And we have to work on building a machine which is capable, if I have, let's say, 300, which was the point on the far right of this graph, if I have 300 of those, let's say, perfect qubits, I can represent more data than there are atoms in the known universe. Just think about how big such a huge amount of data would be. So that's why I show this little universe picture. Now, let's start and talk a little bit about how to build a quantum machine. So just like classically we have to build transistors, yeah, and the transistors we combine, yeah, in particular ways, well, we have to do the same thing physically. We have to work on making those qubits, and we have to make sure that these qubits are stable and live long enough in time, yeah, because we're here, yeah. There was this one Australian, it's an Italian working in Australia, and he was capable of making 1 qubit, yeah, in silicon, in 28 silicon, whatever that is, and it could live for 5 seconds. Everybody's like, wow, incredible. And how can you make 2? No. Maybe 3? No. Okay, so he doesn't know, has no clue how to scale this up. And most likely that's a direction that we are basically not looking at. So in Delft, yeah, because I'm Flemish, but I work already for quite some time in the Netherlands. Yeah, we work basically on quantum dots, NV centers, semiconductors, and superconductor kind of technology. We do not work on ion traps, which was very popular and is still very popular, especially in the US. But we don't have anybody in Delft doing that. And I personally am more on the quantum dots and the superconducting qubits. Now, how do you start doing such work? Because I'm a classical engineer, yeah, I'm a computer engineer, so I'm used to building machines. And then we had the request from the rector, yeah, of our university said, yeah, but we started a new research center called QTech, yeah, quantum technology, whatever is in the name, yeah, and I want you from that faculty, from the electrical engineering faculty, to be responsible for, yeah, making the architecture. I said, like, okay, quantum physics, yeah, well, do I know anything? I have the basic principles like I just explained. And then I started looking and said, okay, I have to start somewhere. And the first drawing I made was actually this one. Was not that sophisticated as I was here, right? It was just with pen and on paper. And this is a system stack of a classical machine. And I said, well, if I simply write the Q in front of each layer, maybe that's good enough, yeah? Well, turns out, so far, this is the case, yeah? This is the case, yeah? Well, we can be proven wrong, yeah? And then I will come here and say, I was completely wrong, excuse me for that, yeah? But for now, this really seems to be, yeah, the key path, and turns out, yeah, just it's a little bit no, I don't know. So, turns out that Intel was at some point every 4 or 5 years, this American that you most likely know, yeah, revises its roadmap, technology roadmap, and quantum was always out. They said, nah, that's too early. That's too early. Yeah, we're absolutely not interested. Yeah, it hasn't matured in any particular way. Yeah, until the last time, and this was like 3 years ago, there was a guy, Jim Clark. Yeah, I can mention his name now, right? He was traveling all over the world. Literally, all over the world, visiting every single research lab working on quantum technology, quantum computing. And that means, you know, the Ivy League universities in the US, right? From MIT, Princeton, Stanford, those kind of things, to Australia, to Canada, all over Europe. And he also came at some point to Delft. And they asked me, together with my colleague Edouard de Charbon, hey, can't you guys say something about quantum computing? Now, happens to be, this is a little bit of interior information. 3 weeks before, we were completely killed because of this idea. By my own rector, by my physicist, said like, what the hell are you doing? Go back to your office and think again and come back. So we said, what story are we going to bring to Intel? And I said, you know what? We don't know anything else. We'll just give this one. Yeah? And remember what happened? They said, no, I was going to say dirty words, so I have to filter myself sometimes, right? Said, like, we have never heard this story. I've been traveling to every single research lab in the US, in Canada, in Australia, in Europe, and this is the only place where I get a systematic and a coherent view on how to build a quantum computer. I said, I don't know. Yeah? So, and that was the start. That was the start. Now I'll show you. Yeah, vanity, of course, has its price. So I'll show a little picture. Yeah, where we started actually working with the Intel people. So again, the system stack we have, and then you have to again start at the lowest bottom. So the dark blue plug that you saw was basically where all the physicists anywhere in the world are working. Yeah. Okay, time is out. Okay. So this is a quantum circuit. So on the right you see, yes, you're right. Yeah, you see a quantum circuit consisting of a couple of operations that classically you do not really use. And that's fine. We know how to use them. And that's, I think, for now, the most important part. Then we came up, this was also a drawing that I showed this Intel person. I said, yeah, I think we need all of these things. And again, the little box, the pink box on the right, is where the physicists are. So that's 99% of the people that are working on it are in just this pink box at the right, and we do everything else. Yeah, and well, actually, that's a team in Delft that is working on that, and so you have to define also. You need to have programming languages. You need to have algorithms, of course. So you need a language, you need a compiler, you need to build all these things. You need to have a microarchitecture. And again, as you can see, we're working on 3 different kinds that I'm currently working on 3 different kinds of physical technologies. And so we have prototypes at least this year for the spin qubits and the transmons. And yeah, we're not so good in making publicity, so maybe being here today is a good exercise. Yeah, and this is my team that works on all of these aspects that I've been telling you. The people at the bottom are PhD students, and at the top are postdocs or assistant professors, and the old guy on the left that's me. Yeah, and then whom else is working on? As I said already, it's a pretty big field these days, and so yeah, on the right you see the American companies. We know Microsoft was on if you read the redactie.be, I don't know whether you do that. Yeah, I do that from time to time. On Wednesday or Thursday, I was like, Microsoft is busy announcing the big quantum computer. I said, huh? Yeah, I said like, yeah, we're running behind. It's absolutely not true, right? So the most famous one is maybe DWave, which is a Canadian company, and they claim to have already more than 2,000 qubits. Is it any powerful? No. My laptop runs smarter than their quantum machine. Oh, and here you do see the picture of Intel when we started. Yeah, that's. I'll just. Now, what do we? Yeah, yeah. I'm running a bit late, but I think that's fine, right? Yeah. Because the people listening to me said, yeah, but you have to talk much more about what are you going to do with it. So this is the part that I will insist on a little bit, right? So why do you need quantum computers? Yeah, we know, of course, the compute power now, yeah, we believe you, yeah, sure, that's fantastic. But how are we going to use that? Yeah, the language that you developed, wow, great. Yeah, but what kind of problems? And then you see an entire domain, yeah, and the big data is a big field, right? I mean, big data, they slap us around the ears with big data every day, yeah, and we don't have solutions for that. Well, wait until we have a quantum computer, of course, yeah? Now, what I personally believe, and I will not go into too much detail, what I personally believe, and we started working on this already now, is working on what is in the top left, yeah, what is on chemical applications, and mostly, yeah, what we start now is on genome sequencing. So genome sequencing, what? I said, you're talking about physics and now it's suddenly biology again, right? But genome sequencing is the future of medicine. So whatever is going to happen, let's say in 10 years, when you go to your physical doctor, yeah, he's going to take a bit of blood or whatever, and he will send it through such a sequencing machine, and then it needs to be analyzed. Now, this is billions of bytes that you need to process. So it takes for one person, yeah, it takes a very, very powerful computer network for more than a week for one person to do one analysis. So that's one thing that we think is an important application domain. So just to give you another example, and then I will really wrap it up. Yeah, is this one. Is about factoring a large number. And this is something that we all use on a daily basis. Whenever you contact your bank, yeah, it's basically in an encrypted way. So that means that the data, you don't send zeros and ones, you send them in an encrypted way. And the encryption basically boils down to, yeah, finding the prime numbers. Yeah, when you multiply all those prime numbers, it gives you your big number, and that's kind of the key, yeah, to do it. So again, if I'm assuming that I have the most powerful supercomputer, which is Chinese, by the way, right? At the Changhe here, and I can build a data center the size of Germany and the Netherlands. So that's around 400,000 square kilometers. Yeah, and just assume that every single meter, yeah, is filled with this supercomputer. It's still going to take me, let's say, about 100 years, €1 trillion, and basically it can never work. But it's going to consume so much power that the Earth is running out of energy in 1 month. So that's not something you can actually see as a realistic approach. Now, if I can build a quantum computer, yeah, and look at the 5 billion qubits, yeah, the physicists, they're very proud, they're at 7 and 17, yeah, so going to 5 billion is still quite a way to go. But in principle, at that size, with the factoring, the Shor's factoring algorithm, it should be done in a bit more than a day. So just to give you an example, from 100 years, yeah, which is with inconsumable amounts of energy, you can downsize it to 1 day, and it really uses much less energy. I did not insist on that, because I'm already running out of time. I will be very short here in the conclusion, that of course there are a number of huge challenges that we still need to overcome, and scaling it up is actually the biggest one. I can make 7 qubits, 9 qubits, 17, and they're always like odd numbers, so don't ask me about those odd numbers, but yes, they are odd numbers, but the potential benefits of building such a machine are so huge that I personally think, and many people, that the investment is really worth the effort. Thank you very much.